Elastic potential energy. Energy can be stored in a spring by compressing or stretching a spring. This energy is called elastic potential energy. Robert Hooke, a contemporary of Sir Isaac Newton, first observed the relationship between the force necessary to compress or stretch a spring and how much the string was compressed or stretched. Hooke's law describes this activity. K is the spring constant. It is measured in newtons per meter. X is the change in the length of the spring. It is measured in meters. The minus sign, that's very key right here, indicates that this is a restorative force. It acts in the direction that would restore the spring to its unstretched or uncompressed length. The relationship is based on the change in the length of the spring. It is the same if the spring is made longer, stretched, or shorter, compressed. The force required to stretch or compress the spring is equal and opposite to the restoring spring force. So here's Hooke's law. This is the restorative force. This is the force that the spring exerts on whatever you've got attached to it. And this is the force you would need to stretch the spring. And it's equal and opposite to the spring force. So the graph here shows the relationship between the force that you're using to stretch or compress the spring and the elongation or compression of the spring. The mathematical relationship can be experimentally confirmed. So the bigger the amount of stretch or compression, the larger force you need. That's what this graph is showing here. And this is for this guy here, the force required to stretch, which is F equals Kx. So we're about to say that the slope of this line is going to be K. So let's vary the displacement or the elongation, the x. So here, this graph, we have a small elongation. What do we have? 1, 2, 3, 4 units. And the force is this amount. Let's not worry about the exact number now because we didn't even tell you what K is. If we have a large elongation, right, 1, 2, 3, 4, 5, 6, 7, 8, go up to the graph, goes all the way over here, you have a larger force. Large elongations require large forces, and small elongations require small forces. And the same goes for compression. The spring constant measures the stiffness of the spring. The spring constant is the slope of the line. Because if you have an equation like this, it's very similar to the equation of a straight line, right? Y equals mx plus b. In this case, b is 0, you start at the origin, and K is represented by the slope of the line. The work needed to stretch or compress a spring is equal to the area under its force versus distance curve. So here's the force, here's the F equals Kx curve, and what do we have here? We have a triangle. So the area of a triangle is 1/2 base times height. The base is x and the height is force. The force is equal to Kx. Multiply through and we get the work done in compressing the spring or stretching it is 1/2 Kx squared. Now use the work energy equation where the initial unstretched energy is 0. So we have E0 plus work equals final energy. So we have work equals the final energy of the spring. The final energy, E sub F, stored in the spring by the work done on it is the elastic potential energy of the spring. EPE equals 1/2 Kx squared. Like all forms of energy, it is measured in joules. The elastic potential energy is directly proportional to the square of the elongation, right? That's x, and you square it. Stretching the spring twice as far requires twice the force, right? Because F is Kx, but 4 times the work because you have to square the 2. Here's an interesting graph. Let's say here we have F equals Kx versus x, and we do 1 work unit here, okay? We stretch it a distance 3. Now we're going to stretch it a distance 6, okay? So the first thing we notice is this force is twice what this force is. Second thing we notice, we take this triangle here it's again, and we can put 3 similar triangles over here for a total of 4. So that's 4 work units. So what we're showing is the force doubled, and the work went up by 4 times when we doubled the displacement. Elastic potential energy is directly proportional to the value for the spring constant. Smaller displacements require different amounts of work. The large spring constant requires more work and stores more elastic potential energy with similar elongation. So let's say we stretch both of these springs out to this distance here, which is the same. For a small spring constant, and remember the spring constant is the slope of that line, you have this much work done, this much energy stored. For a larger spring constant, you have more energy stored. A spring with a spring constant of 120 newtons per meter stretches by 0.050 meters. What is the potential energy of the spring? We have our givens right here, and then here's our EPE equation, 1/2 kx squared. We substitute in k and x and make sure you square it, and we get EPE is 0.15 joules. An elastic spring stores 45 joules of potential energy when it is stretched by 2 centimeters. What is the spring constant? We start with our givens, and the first thing we do is convert the displacement, the distance it's stretched, to meters. We then have our EPE equation. We solve it for k by multiplying both sides by 2 and dividing by x squared. Then we substitute in our values here, and don't forget the square there, and we get k is 2250 newtons per meter. A spring with spring constant 80 newtons per meter has 0.10 joules of EPE stored in it. How much is it compressed? We start with our givens listed right here and the EPE equation, and we need to solve for x. So we multiply both sides by 2, divide by k, and then make sure you take the square root because we found x squared here, but we need x. So x is the square root of 2 EPE over k. Substitute in our values, and we get x is 0.05 meters.